So let's look at some acid-base chemistry for organic 201. And our acid-base chemistry has centered around two main theories. The first one we want to recap is the Bronsted-Lowry theory for an acid and base. And the Bronsted-Lowry theory tells us that an acid is a chemical which donates protons during the course of the chemical reaction. So if we take a look at an example, the reaction between hydrochloric acid and ammonia, and we can track how the two chemicals change over the course of the reaction. The HCl becomes just H, and the NH3 becomes NH4. We can improve the picture a little bit if we add in some electrons, the lone pairs, so we can see where the octets are. But that act of breaking the hydrogen to chlorine bond, effectively giving the hydrogen away, makes the HCl a proton donator and an acid. The NH3, for its part, it's picking up that proton from the acid, and chemicals which pick up protons are bases, according to the Bronsted-Lowry theory. Bases are proton acceptors. So there's our first one. Let's take a look at another example which fits the Bronsted-Lowry theory. We'll look at another reaction. This time we'll add in the lone pairs immediately. And as we look at how these chemicals change, the H2O changes to its conjugate H3O plus. So over the course of this reaction, it's picked up a proton. As we just said, chemicals that pick up protons are bases, according to the Bronsted-Lowry theory. Meanwhile, the HNO3, by the time it turns into its conjugate, it's lost that hydrogen, lost the proton. And of course, that's the role of an acid, according to the Bronsted-Lowry theory. Let's take a look at one more with the Bronsted-Lowry theory. We have got the alkyne with the sodium amide. And if we look at what happens over the course of the reaction, let's put in the lone pairs where they are. The nitrogen with two lone pairs for the amide ion. And then the product here has a lone pair of electrons, making it negatively charged, attracting the sodium metal ion. So for this alkyne, by the time the reaction finishes, it's given away the proton. It's acting as a Bronsted-Lowry acid. And the sodium amide, it is going to pick up that proton, which causes the sodium to drop off, but still picking up that proton, being a proton acceptor, like a Bronsted-Lowry base. So in the Bronsted-Lowry definition, the acid is the proton donator. It's going to lose hydrogen over the course of the reaction, while the Bronsted-Lowry base is the proton acceptor, and it's going to gain hydrogen, gain protons over the course of the chemical reaction. Now let's switch gears and look at some examples of the Lewis theory for acids and bases. And of course, for a Lewis acid, we say that a Lewis acid is an electron acceptor. So let's look at an example reaction where we can see that at play. So again, it's the same reaction we had before, but we're now going to look at it from the point of view of what's happening to the electrons in the chemical reaction. So the HCl breaks its chemical bond, and as the bond breaks, the electrons are picked up by the more electronegative element. That's the chlorine at 3.0 compared to hydrogen's electronegativity at 2.1. Unless something really weird is happening, the more electronegative element picks up the electrons. So we can say that chloride is accepting the electrons. It's playing the role of the acid. Meanwhile, for the NH3, which we know from the Bronsted-Lowry theory is a base because it's about to pick up that proton from the acid. And as we look at the electron flow, it's specifically picking up those electrons because it uses its lone pair to initiate the chemical bond. That's why the HCl bond breaks, so we maintain the duet for hydrogen. So in the action of making that new bond, is giving up control of that lone pair, and it's going to share that lone pair of electrons with the hydrogen. And this is the role of a Lewis base. Any chemical which donates electrons over the course of the reaction is a Lewis base. So an acid is an electron acceptor, a base is an electron donator. Again, let's look at another example, this time between water and HNO3. Again, the same reaction that we had just looked at from the Bronsted-Lowry theory, but now we're examining it from the point of view of the Lewis acid and base theory. So we have got a molecule of water which is going to turn into H3O over the course of the chemical reaction, and it does that by picking up a proton from the HNO3, and it specifically does that by donating its electron pair to make the new chemical bond, donating its electron pair and acting like a base. From the point of view of the HNO3, as that proton is plucked away, as that happens, the electrons in the chemical bond between the hydrogen and oxygen retreat back to the oxygen. We can say the molecule is accepting electrons as that bond breaks, and an electron acceptor, of course, is the Lewis acid. Let's look at our third and previous example with the alkyne and the sodium amide. Now again looking at it from the point of view of the Lewis acid-base theory. So that chemical bond between the carbon and the hydrogen is going to break, which allows the alkyne to release the proton to the amide. But the very action of releasing the hydrogen, that proton, sends the electrons in retreat back to the alkyne. It's accepting electrons and acting as an acid according to the Lewis theory. The sodium amide, picking up that proton, has to use one of its lone pairs, and so it's effectively donating its lone pair to make the chemical bond happen. And of course that's the role of a Lewis base. So interestingly, many of the acid-base reactions that we look at can be viewed from the point of view of the Bronsted-Lowry theory and from the point of view of the Lewis theory. But there are some special examples where perhaps only one of the two theories applies. Specifically, sometimes only the Lewis model applies as an acid-base reaction. So again, let's look at some examples of this. So this time looking at an aldehyde reacting with the methoxide ion. And let's look at how the electrons change hands over the course of the reaction. We have made a new chemical bond by the end of the reaction. We can see it here, and it gives us the clues that we need to realize how this reaction has taken place. There's a new chemical bond here between the oxygen and the carbon, and that chemical bond must have taken place by using an electron pair on the methoxide from the oxygen, donating its electrons to make the new bond to the carbon happen. Of course, to maintain the octet, as that pair of electrons comes in, the pi electrons would have to recoil back. We must maintain the octet for the carbon. So looking at the role of each chemical, having used its electrons, having donated electrons to make the bond, The methoxide is acting as the base, and the aldehyde, having received the electrons, accepting electrons, is acting as the acid. But it's only the Lewis model which describes this reaction as an acid-base reaction. There is no proton transfer, and so we can't use the Bronsted-Lowry theory. Let's look at another. This time a secondary amine reacting with borane. Keep in mind with borane, specifically the boron atom in borane, we have got an empty atomic orbital above and below the plane of the sp2 hybridized boron atom, and that empty orbital is really good at accepting electrons, and that's exactly what the boron does, and we get this new chemical bond between boron and nitrogen. So that bond occurred because we used a lone pair of electrons on the nitrogen, supplying electrons, and the new chemical bond forms, and the supplier of electrons, the donator, of course, is the Lewis base, and the acceptor of the electrons is the Lewis acid. So we can say that the Lewis model describes more acid-base reactions because it's a stronger definition for an acid and base and covers a much greater range of reactions. So any reaction which can be described as a Lewis acid-base reaction could be described as a Bronsted-Lowry acid-base reaction as well, but not all the time. There are some acid-base reactions which can only be described as a Lewis acid-base reaction because there isn't a transfer of a proton. That's the basis for the Bronsted-Lowry theory, that proton transfer between the acid and the base. So let's look at some last additional examples. First one, looking at a ketone reacting with ethoxide this time. And pause the video for a second and try this one for yourself. Think about how the chemicals have changed over the course of the reaction, where the new chemical bonds are, and any chemical bonds which have disappeared, and think about how electrons must have been donated or accepted to make those chemical bonds happen. So looking at the changes in chemical bonds by the end of the reaction with our product, we see that there's a new oxygen to carbon bond here, and so we also see that the carbon to oxygen double bond has broken, probably because of a recoil effect, because a lone pair of electrons comes in from the ethoxide, specifically the oxygen, donating its electrons to make this new bond to the carbon happen, as we had already highlighted in yellow. And to maintain the octet for the carbon, those pi electrons have to recoil back. So the aldehyde, accepting electrons, is acting like an acid, and the ethoxide molecule, donating its electrons, is acting as a Lewis base. And it's only the Lewis definition which fits for this acid-base reaction. An exchange of electrons, but there isn't an exchange of protons. Let's look at one more before we finish up. This time an aldehyde again reacting with the ethoxide, and let's look at where the new chemical bonds are appearing by the end of the reaction. There's a new carbon to oxygen bond, a single bond that used to be a carbon to oxygen double bond. There's also a carbon to carbon double bond that used to be a carbon-to-carbon single bond. And then finally, an oxygen-to-hydrogen bond that wasn't there before. We've got the ethoxide, and it's turned into an alcohol by accepting that proton. So this must have been the starting point for the chemical action. A pair of electrons from the ethoxide stretching out to pick up a proton, and this is the only place that the hydrogen could have come from. We've got 1, 2, 3 hydrogens at the beginning because it's a terminal carbon, but with that double bond to make up the octet, there's only 2 hydrogens by the end. So let's put in that hydrogen, which is about to be moved over. That pair of electrons again from the ethoxide, it's donating its electrons and it's picking up that proton. As that happens, to maintain the duet for the hydrogen, this existing chemical bond has to break. The electrons are sent back to the carbon, and it uses them to make a new carbon-to-carbon pi bond. And to maintain the octet for the apex carbon, that carbon to oxygen pi bond has to break as the electrons retreat. So looking at what's just happened, we've got this molecule accepting electrons, these electrons here, as the hydrogen breaks off, accepting electrons, which makes it a Lewis acid, but it's also giving a proton away, which makes it a Bronsted-Lowry acid. And the ethoxide donating its electrons, making it a Lewis base, but it's also picking up the proton, making it a Bronsted-Lowry base. So for this second reaction, both the Lewis and Bronsted-Lowry theory hold true.